Okay, we now want to look at the issue of current and develop the idea of current into Ohm's law. Okay, so first of all, what is current? Current is the flow of charge, right? Anytime you have charged particles moving in any manner, that is defined as a current. Mathematically, we define current um, with the algebraic variable I, and we define current to be the amount of charge delta Q that flows past a given point in a time interval delta T. Okay. If you take these over a short enough time interval, then of course this becomes a derivative in the limit as delta T approaches zero. For a lot of cases, especially steady current states, in those cases, then this definition will do just fine. When you have the current behaving as a function of time, you will in fact need the derivative. Okay, but let's develop an idea of what current is. So imagine you have some wire. We don't care what it is. All we have to worry about is whether the wire is conductive. Okay. So imagine you've got some conductive wire. And the reason we need good conducting wires is when you apply an electric field, right? So suppose you have an electric field. We aren't going to worry about what generated the electric field for the moment, okay? But if you have an electric field, and then suppose you have negatively charged particles, okay, and why do we need negatively charged particles? Well, because it's the negative charges, it's the valence electrons in your conducting materials that contribute to the current. So when you go to the periodic table of elements and you look at your classic conductors, things like iron and nickel and copper, these are located in what are called the transition metals. And it's the atomic structure of these metals that allow your valence electrons to not be terribly bound to their parent nucleus. So when they feel an external influence, like an electric field, they're very easily stripped off of their parent atom and then can move through the material rather freely. So these atoms typically will contribute one or two valence electrons to the overall current per atom. Okay. So you're not stripping off, all 26 of an iron's electrons. You're stripping off maybe one or two. And then the material still carries a zero net charge because you're not removing the atoms from the material. You're just removing them from a given parent nucleus. Okay, but the material itself remains electrically neutral unless you're ripping the electrons off into the air. But when you have things like current moving through a wire, that generally doesn't happen. It can happen under certain circumstances, but it generally doesn't happen. If the electric field is pointing this way, okay, like toward the right here, as in the diagram, then our electrons are actually going to drift this direction, right? The electrons are going to drift opposite the direction of the electric field. And these carriers are going to drift with a velocity VD, and we'll kind of give a qualitative estimate of what VD is. Okay. Um, but to start, let's look at this quantity delta Q. If I want to count the total number of charges that move past a given point, so for example, if I have a really super duper microscope that can actually see the flow of charge, and I just label this line as my quote unquote line of observation, and I count how many electrons move past that line in a given time interval, then that's what I'm going to label as my value of delta Q. Okay. So delta Q you can think of as the number of charge carriers times the charge per carrier. Now, if my charged particles, my individual charge carriers are electrons, then the charge per carrier is going to be the elementary charge on an electron, right? And remember that that is 1.6 times 10 to the negative 19 coulombs, okay? Now, what about the number of charge carriers? We can label this value as n, capital N, for the total number of charge carriers, but we won't use that number. What was often used instead is going to be the number lowercase n, which is called the charge density or particle density is probably more a appropriate. And the particle density is equal to the number of charge carriers per unit volume. Okay, so it's equal to the total number of charges that are free to move in a given volume. Now, what is the volume that we're interested in? Well, the volume of a cylinder, if I have a wire, is going to be equal to the cross-sectional area of one of the faces multiplied by the length delta x, right? So this is equal to n over a times delta x, right? So if I want to substitute this type of expression in for n, then n is going to equal little n times a times delta x, right? So my total number of charges, delta Q, is going to be equal to my charge density or particle density times the cross-sectional area of my wire times the length of wire I'm considering, delta x, times the amount of charge on each individual charge. And I can take this one step further, and I can say, well, what if I look at this over a given time interval and divide delta x by delta t and then multiply all of this by delta t, right? Then what I have is n times a, and delta x over t is the drift velocity, or the speed that the electrons are moving through the wire with, times delta t. And so essentially what I'm doing is multiplying by 1, right? I'm just multiplying by delta t over delta t and then rearranging where the denominator goes. And then I can divide both sides by delta t, and I get Q over delta T is equal to the particle density times the area times the drift velocity times the individual amount of charge per particle. And this is a microscopic view of current, okay? This is a microscopic view of what current is. Now, what are typical speeds for the drift velocity? It turns out that most drift velocities under normal circumstances, okay, when you have everyday household type voltages causing typical type currents on the order of maybe say amps to tens of amps, um, these are going to be on the order of 10 to the negative 4 meters per second, maybe up to 10 to the negative 3 meters per second. Okay. Typical drift velocities inside materials are going to be on the order of that speed. Now, you can have currents that are have drift speeds faster than that. For example, lightning will be faster than that. But inside materials like copper, nickel, etc., these are typical values at which the electrons move. Now, um, compare that with the speed of light. Okay, so the electric field, however you establish said electric field, in our cases, most often we'll do it with a battery. But when you establish an electric field, um, that electric field propagates through your material at the speed of light. Okay, but your electrons don't move that fast. The signal that tells them to start moving does, but the individual electrons will only move at this drift velocity, which is dependent on the specific density of your material. But again, your typical values are going to be on the order of, say, um, uh, tenths of millimeters per second or millimeters per second or so. Okay. Now, if I look at a cross-sectional area of wire, right? So if I kind of magnify this view a little bit from what I had on the last page, and we have our electric field in here, okay? I know that I'm going to have negative charge flowing through this face, right? I know that I'm going to have a negative charge flowing through this face. And under the initial assumption that the current is uniform with respect to position within the wire, in other words, we don't have any radial or angular dependence. We don't have more current up at the top than we have at the bottom, or we don't have more current on one side than the other side. Everything is flowing uniformly. Then this leads to the idea of current density. Okay, so current density we denote as J, and current density is equal to the current at a point in your wire divided by the cross-sectional area. Okay, but from the previous slide, we know that current is equal to N times A times the drift velocity times Q. And so if I take that expression and divide that by A, this becomes N times VD times Q. Okay? But your drift velocity is a vector, and therefore your current density is a vector as well, right? And if you look at it in this form, it turns out that the vector nature comes from the fact that areas also contain a vector direction, okay? Um, and so your current density is just the total amount of current or the flow of charge per unit surface area. Okay, and when I say surface area, we're talking about the face of a cross-sectional piece of wire, not the actual surface of the outside of the wire. Okay, so it is the cross-sectional area of the wire that we're interested in here. Now, current will flow more easily in materials with what we call a high conductivity. So there's a value called sigma that is equal to the conductivity of a material, and materials with high conductivities allow current to flow more easily. And it turns out that your current density J is equal to the conductivity times the electric field established inside. And remember that your electric field is here. But to have an electric field means that you've established a potential difference between the two ends of your wires. Right? And so the potential difference between those is equal to the field times the length of the wire. And so your current density is also equal to sigma times delta V over L. Okay. Now, your current density J is equal to, remember, the current divided by the surface area or cross-sectional area. I really should say cross-sectional area. That's a little more specific. And this is equal to your conductivity times the um, potential difference divided by the length of the wire that is in question. Okay. Um, and what I can do is now look at this equation. Okay. I can look at this equation and I essentially want to get a relationship for or a relationship between delta V and I. Okay, I want to develop a relationship between delta V and I. And so what I can do then is say delta V is equal to I times the length divided by the conductivity times the cross-sectional area, right? But there's another quantity called the resistivity, not to be confused with charge density, but this is the resistivity. And this is a measure of how resistive your material is. And it turns out that your resistivity is equal to the reciprocal of your conductivity. So if you have really good conductivity, you'll have very low resistivity. And if you have really high resistivity, you'll have very low conductivity. And if you think about it, that should make some sense. Because a very high resistivity means that your material is approaching an insulator and it should not conduct very well. Whereas if you have a very high conductivity, then that means your charges flow very easily and your material should be a very poor insulator and it should have a very low resistivity. So, with this definition, what we can say is that I is equal to rho L over A. Okay. Now, this quantity, rho L over A, this is the quantity that we call the total resistance. Okay. This is the total resistance in your material. And this value, the resistance, is in ohms. Okay. Your resistance is measured in ohms. And if you think about it, this formula should make some sense. You have some material, whatever it is, it doesn't have to be an iron or copper wire, but it can be. And the longer you make your material, the more atoms you put in the way of any given path. And so, the longer you make your material, the more atoms there are for each individual electron trying to flow to bump into. And that is essentially the root of what resistance is. The more material that will impede the flow of your electrons is a higher resistance material. But the larger you make your cross-sectional area, or the larger you make your wire, the more space there is for the electrons to flow through. So it should make some sense that the longer you make your material, the more atoms any given electron will have to bump into. But the wider you make your material, the more space each electron has to flow. And so it should be proportional to the length, but it should be inversely proportional to the area. So with that in mind, your resistivity rho, if your resistance is measured in ohms and your length is measured in meters and your cross-sectional area is in meters squared, then your resistivity should be measured in ohms times meters. And we give the symbol omega, the Greek symbol omega for ohms. So resistivity should be measured in ohms times meters because the L over A quantity will be in 1 over meters. Okay. So what this result gives us is the expression for Ohm's law in its popular form, delta V equals IR, or potential difference is equal to current times resistance. Okay. Now, most regular circuits will look like this. We're going to have circuit diagrams, and in our circuit diagrams, 4 bars, 2 large ones interspersed with 2 small ones, are going to represent a battery that is the source of our voltage, or our voltage source. And then just regular lines connecting our different elements are going to be assumed to be ideal wires. And so when we say ideal wires, what we're implying is that the wires themselves don't really contribute any resistance. Okay. So ideal wires in our circuit diagrams have a resistivity of 0, but this squiggly line represents a resistor. Okay, so when you put a resistor in the path with ideal wires, all of your resistance is going to be wrapped up in this resistor. And so you have a resistor R, you have a voltage source delta V, and you can put an ammeter in your circuit to measure your current, right? And Ohm's law says that your potential difference in a simple circuit should equal the current that you measure with your ammeter and multiplied by the resistance or the value of your resistor in ohms. Okay. Let me spell ammeter a little bit better, more clearly. Okay. So current, okay, current is charge per time, and we give this the unit of amps. Okay, so current is measured in amperage or amps, and that's why the instrument used to measure it is called the ammeter. And so, if you think about this will give you some intuition about what an ohm is. Okay, so resistance is equal to potential difference divided by current. But remember what potential difference is. Potential difference is potential energy or joules per unit charge or coulomb, and current is coulombs per unit time. Okay. Um, and maybe I should use seconds here since we're using joules, coulombs, and so forth. And so what an ohm is equal to is joules times seconds, or energy times seconds divided by coulombs squared. Okay. Now, that might not be terribly intuitive. That might not, really tell you anything. But if you think about um, energy being distributed uh, per charge, okay, energy being distributed per charge, over a given time interval, but not divided by the time interval, multiplied by that time interval, over an extra charge, then that is the picture of what the ohm is. And again, I'm not 100% sure if that will give you some intuition, but that is what the ohm is in its um, not quite base units, because the joule is newtons times meters, or force times distance. But in somewhat pseudo base units, if you will, that gives you what the value of the ohm is. Okay. So this is your basic circuit. Okay, this is your basic circuit. V equals IR. And in the next set of videos, we will do some interesting examples with this. And I'll also go over some examples on how to calculate things like the uh, current density. We will do some explicit examples involving J. We will do some explicit examples using Ohm's law. And then we will apply these to complex circuits where we have multiple elements in our circuits. Okay, so we will see you next time.